is the magnetic field in the coil proportional to the current in the coil? What equation tells you the answer is absolutely yes? Bunny. B of a coil is equal to mu naught n, little n, number of turns per unit length, times I. Bunny. Yes, it is. So it makes perfect sense that the back EMF is proportional to, instead of d phi b dt, instead of the rate of change of magnetic flux, it makes perfect sense that the back EMF is proportional to the rate of change of current, which is, it happens to be a lot easier to measure than the rate of change of magnetic flux. So this is great for us. Now what we are going to do is we are going to define this thing called inductance. We use the symbol L for inductance. This thing right there is inductance. If you simply define the inductance for any circuit, there's our definition symbol, as the magnetic flux you get
through the loop
per unit of current. So flux is measured in Teslas times what? Meters squared. Flux is B dotted on A, or the integral of B dot dA. So this flux is measured in Tesla times square meters. By the way, that is also called a Weber. A Weber is simply a Tesla times a square meter. So the inductance can be measured in Webers per amp, or Tesla square meters per amp that you get. So for a coil, it's going to make sense that our inductance of a coil is the number of turns times the magnetic flux through the coil per amp. So for a coil, the inductance defined this way. Same as over here, as long as you remember that when you have more than one turn, it's kind of a similar idea. You got to count that flux for every single turn. Well, you multiply it by capital N, the number of turns in your coil. Now, L is very analogous to mass. The higher inductance means there's more tendency to retain the same current.
For example, when you try to accelerate a mass, the force on you is proportional to the amount of mass that there is times the rate of change of velocity. Now, why is that negative sign in there? Because that's not the force on the mass, that's the force on you. When you exert a force on a mass, it exerts a force back on you the opposite way. So the force on you is proportional to the mass that you're trying to accelerate and proportional to the dv dt, the rate of change of velocity. Similarly, if you try to change the current in a coil or in a loop of wire, then the back EMF, the electromotive force, not a force but a electric potential, is proportional not only to the inductance, which is just like mass, but it's also proportional to the rate of change of current. So when you take a mass m and try to change its velocity at a rate dv dt, you will get a force, in fact you could call it a back force on you, of negative m times dv dt. That's just like if you take an inductor of inductance L, also called self-inductance L, and you try to change the current in it at a rate di dt, you will get a back EMF of negative L di dt
across the coil. The coil will
try to push back on any changes in current.
The back EMF is negative L di dt is the back EMF. But L is a constant which depends on the geometry and physical characteristics of a circuit or a coil. It's called inductance, also called self-inductance as well. And what does this remind you of? Something that depends on geometry and physical characteristics. Capacitance. And you'll see that it is a very awesome counterpart to capacitance. It also stores energy, but in a different way. And it has also, when you charge, so-called charge an inductor, it also has a time constant, as we will soon see.